Helen here?
I think she's here. So let me what I'm going to do next first is try to talk about the quiz a little bit, like the midterm a little bit. So I guess you guys are doing quite well, but like I still like go through some of the questions maybe. So I guess the first question maybe I make a new page here. So the first question we say like there's some students, like 1,000 students, and the average weight is 130 pounds, and then like basically I have a coordinates given to use like that, and then the average height is like 170. Then the first question is like asking you like what's the maximum weight of the lightest 10%. So this is a little bit tricky question actually. This is similar to what we kind of talk about in class, but there's something different. Like the lightest 10% average. So I have 1,000 students, right? So then, and now if I think of like splitting these students into 10 groups here, first I sort all students here, right? I sort the students into descending order in according to their weights. So then afterward, let's say I have group 1, group 2, and I have 10 groups there, right, up to group 10. Then what you can observe is like apparently the average of one group, like group 1, will be at least as heavy as the average of group 2, right? So group 1 has to be like heavier than group 2. Or like no less heavy. The mean of group 1 will be like heavier than the mean of group 2, and so on and so forth. So therefore, if I have 10 groups here, actually I'll ask you what's for this last 10%. This is basically group 10, right? What's the highest weight for this group? In this case, actually simply just 130, right? Yeah, because if this is more than 130, all the rest will be at least 130. So if this is more than 130, then all the rest will be more than 130. So therefore, the mean will be larger than 130. So that's the first question. And the next couple questions is pretty simple. I guess I won't go through that. Like maybe just for the D part, like because I basically, for example, I asked you what's the number of bits I need to store for the weight or the height like separately. Like for the weight, for example, it would be just 1/2 log 2 pi e. The variance is just 10, and then I have log delta as the in terms of number of bits, right? So yeah. So but if I can store them together, then just be careful that I should compute the joint entropy instead. So it's 1/2 log determinant 2 pi e and that sigma, and that's will be the amount of information minus log delta, number of bits needed to store both like the weights and the heights. That will be like the D part D. And then let's see, for the second question, this is pretty straightforward. I'm not going into that basically, and it's very much similar to the homework problem, at least except that like I forgot to specify in the question that like I want to ask you guys to consider a general case that the probability of winning for team A and team B may not be the same. And some of you guys just assume to be the same because I didn't specify that. I didn't deduct you for any mark and any score and any points. But for you guys to consider the general case, I just give you an extra bonus for that. So and that's question 2. And question 3, again, is very similar to the homework problem that I have. Someone is throwing a fair dice for like 10,000 times, and then the average outcome, let's say average, of course if I don't ask you what's the average outcome should be 3.5. If I don't give you any constraint, that the expected average is just 3.5, right? That's basically 1 plus 2 plus 3 plus 4 plus 5 plus 6 over 6, right? Will give you 3.5 there. But now if I restrict you to be like bigger than equal to 4.5, then you know that like if I use the conditional limit theorem, so on, and then I will have the form of the solution will be like 2 to the lambda I over 2 to the lambda I sum over I equal 1 to 6, something like that. This is the probability of like getting I, right? Then you just like fit into and we know that like if I ask you like if we constrain that the outcome is like bigger than equal to 4.5 by conditional limit theorem actually exactly equal to 4.5, then we can try to find like what's PII such that this is equal to 4.5, and then we solve for lambda, then we'll get the outcome and so on. And A part and B part is basically the same thing. B part will be like saying less than equal to 3 is like different from the homework, but we have the general form is like PI is something equal to 2 to the lambda GI, something like that, right? 2 to the lambda GI. So therefore, like in this case, I should have just GI equal to minus I. Again, I should force lambda is bigger than equal to 0. Of course, if you ignore that, like you just say like GI equal to I, then you will have lambda is like less than equal to 0. Other case, you will solve that, able to solve that. Then again, you will get some numbers there. Actually, this one should give you like total number is 544 ones, and this is total number is 2, 4, 6, 8, something like that. C part, some of you have problem here. Actually, this I doesn't mean that to be tricky, but when your average is specified to be from 3 to 4.5, then basically it's what you expected, right? If that would be the constraint, that would be something like just simply typical, right? So therefore, like you expect the outcome like should be just 3.5, and therefore like the total number of 1 is simply like 10,000 over 6. So yeah, the total number of 1.
But in the range, no? 4, 5,
Yes, there's a range
5, 4,
here.
4.
That's the constraint here, but that constraint can be ignored, right? Because out of this within this range here, what's the most probable one? The most probable one is simply the typical sequences, right? So therefore, like it would be simply the typical case. That is like the uniform case.
The probability more probable.
Yeah, the most probable is simply that the one way. Just only when you are forced outside the typical range there, then you need to use this conditioning limit theorem. So you are in the range that is include the typical one, then what you expect would be just the typical one, right? So therefore, it's just equal to that.
But we don't know the epsilon.
Epsilon, which epsilon?
I mean, like for how many that will be split.
Yeah. Typical. But we don't need that here actually. Okay.
Because that is fair dice. That is fair dice.
Yeah. Because we already specify it's fair dice, right? The typical for fair dice will be just they are all uniform, right?
So then we'll have epsilon in there. Oh yeah.
That is only for proof when you use the epsilon actually. You don't. Yeah. Yeah, you only need that for proof. So let me. Okay, for question 4, question 4 is kind of interesting because this one of my friend colleagues asked me this question, and then 2 weeks before the midterm, that's so nice. Then I just realized this is a good midterm question. I think he need that for some kind of research. I don't know where he needs that, but he's just like needs it somehow. So basically, again, the questions is that he has like some random variable x, y, and s, such that like this is satisfied hs given y is equal to hx plus hs given yx. So he asked me like what will be the under what condition this will be satisfied. So I gave you a little bit easier version. I just used that to show that x and y are independent. So then you know at least like what kind of condition is to satisfy. Like one condition is like one necessary condition is like they has to be x, y, and y should be independent. Wait, I taping right. So now. Now let's look at what we have here. So, okay. First thing, let's realize that. Like, let's move this guy on this other side here. So I have basically this is is given is x given y, right? If I move this side to this other side. I mean, is x given y is equal to hs given y minus hs given y mx. So it's equal to hx here. Now I can rewrite this guy in the other way. So that I can write this as hx given y minus hx given y s and y, right? Yeah, so this is actually. So therefore, if you know what you're doing, this is actually pretty simple. Here you're already done because you realize that by conditioning limit reduces entropy, this has to be smaller than this way. And all entropies has to be bigger than equal to 0. So therefore, like here, I can conclude that like hx given y should be equal to hx, right? And also x given s y is equal to 0.
Yeah, that's right.
Yes. So, and of course this is just saying that like ixy is equal to 0. So therefore x and y are independent. So and then you see like basically like this is satisfied with these two conditions here. So if like x and y are independent, if x is equal okay, x given s and y is equal to 0, then it's
mean that s should be a function of x.
X will be a function of s and y,
yeah.
Or like x will be like at least deterministic given s and y. Yeah, so in a sense it's meaning that it's a function.
Yeah.
So then the second part is just thinking I give you an example is let's say if I x and y outcome of voting to two dices, and of course the outcome should be independent, then s is the sum of them. Then I ask you whether this will be satisfied. Then if you look at the condition, immediately you can see it's satisfied, right? Because x and y independent, so this is checked. Then for this guy here, s is equal to x plus y, that means x is equal to s minus y, right? So therefore like x is a function of s minus y, so again this is equal to 0. So therefore this is satisfied. Okay, for the for the last question is a bonus question. So I just ask you guys to fill in the complete the proof. Actually, I found that that's when I found that I'm typo in the slides, but I guess you guys anyway like able to solve that, some of you, but I deduct you guys some points for those you try, because for most of you didn't actually have a complete constraints here. Actually, like I was a bit sloppy at the beginning. Also, I didn't include all the constraints. So, but basically, like we have constraints like this, right? We have constraints k constraint 1 to big K here, and we have some function gk for outcome xi, the average. Basically, this is the expected outcome. Yeah, actually, it's correct, actually. So what? Oh, maybe I should write like this. Don't write like this. So I have like sum over x-axis as some alphabet. The expectation, basically I have like the expectation of gk x should be bigger than equal to term alpha k, right? I have k constraint, big K, so many constraints here, from 1 up to big K. And then now we basically we want to maximize. Actually, I should minimize the KL divergence, right, between P and Q. P is your
our goal.
Yeah, P is our goal, Q is our prior. But we have some constraints. This is one of the constraints, right?
Yeah.
But there are some other constraints. Don't miss out some other constraints. Basically, we need to make sure that like P are the random variables. They has to be positive, right? For all Pxi, for all x, P has to be positive. And if I sum over P, should be equal to 1, right? And let's see what else. Yeah, that's more or less it. So then if we have all the constraints, therefore like Px this is like KL divergence PMQ minus sum over k into 1 to k lambda k gkxi or gkx px minus alpha k. This is like for this constraint, right? This constraint here. For each of them, I have a lambda k here, right? And I have also constraint from this guy here. I have like mu, maybe I use mu x here, px, and plus nu px minus 1 equal to 0. So if I take partial derivative, it should be equal to that. And I have, basically I need this mu x lambda let's say not then k, yeah, nu, all of them should be bigger than equal to 0. And also like this constraint should be satisfied. So the original constraint should be satisfied. This one, and this one should be satisfied. And we also have the complementary slackless condition. That's this one is equal to 0. This one equal to 0, and this one is equal to 0. And I'm actually I don't think I'm actually, if you take derivative for this guy here, what you have is like take derivative with respect to px here. Here you only left with some lambda k g k x k equal to 1 to k, and this I have like mu x here, right? And I have some nu here equal to 0. And this guy, actually, if you take derivative, is to give you log px over qx plus 1 over log 2. So basically, these are all just constant, right? Something like, I mean, constant in terms of like log. Wait a sec.
That become constant times 2 power log.
Oh, actually, I forgot this. I'm jumping this far too fast. This one I can specify as one thing. Is like, I have this constraint here. I have some mu x here, but remember that like I have also the complementary slackless constraint. That's basically px mu x is equal to 0 for all x here. So therefore, for the x there, like px, there's basically two cases. Either px is equal to 0. Basically, at that particular outcome, that's just, it's never going to happen. Or like if px is not equal to 0, then mu x is equal to 0. So therefore, in any case, this term will be gone. So this is gone. Okay? So therefore, like here, this is constant here. Then I have px over qx is just equal to 2 to the power this lambda k gk p1k times some constant. That constant doesn't matter. I've I move qx up here. Let's move qx up here. So it is basically, therefore this is proportional to qx times this. I have 2 to the, yeah. And then of course I can normalize that, so therefore I have some qx blah blah blah. So anyway, so that is actually pretty straightforward. It's whenever you get familiar with the KKT conditions, it's quite easy. So that's the quiz. So again, remind you guys that you're supposed to submit the abstract like this Friday, and yeah. And let me continue with like the Gaussian distribution, the joint Gaussian distribution. So we kind of I kind of motivated you guys that like what we learned can build a Gaussian process, at least one-dimensional Gaussian process, and so but also in our example, like in my example there, like I kind of assume that like I made an observation. That observation I have 100% like sure. So I observed this guy here, so therefore like this point is exactly equal to that, and then only affect the rest of the variables and so on. But it also happened that you can also model that like you don't have like exact observations, but maybe you have observation. This is just a noisy copy of this point here. So for example, like in that case, think of a simple case here. If I have like pxy, let's say, y is my observation, let's say. This is my observation here. And I have some pi px, and then I have like a distribution like this likelihood like py given xy. So let's say my pi is Gaussian, this is Gaussian, and this is also Gaussian. So what you can see is like here what we need to deal with is a product of two Gaussian PDF. So it is different from like product of two random variables. We are not looking into a product. Be very careful. We are not looking into a product of two random variables. Like we have random variable x and y, and we look at like what's the variable z supposed to be. We actually have like two PDF like for two random variables, and or like just two distributions, and they're both Gaussian, we want to look at like what's the product of these two distributions.
The product of two Gaussian.
Yeah, two Gaussian PDF. So the Gaussian PDF, you remember, is like we have this complicated form, right? So, but it's basically it's like exponential or something. Mu, yeah.
Gaussian also.
Yes, that is kind of, but be very careful. Not exactly, actually. It and this is like one example here. Like, let me motivate you another one. For example, I compute likelihood. This also happen, right? Let's say if I have like y1, y2. So this itself is a likelihood. But let's say I have two observations, observation 1, observation 2. Now, if they are conditionally independent, like I have y1, y2 given x here, right? So this is a kind of representing, for example, I have some, yes, this is some Markov property, but I want to say, for example, this, maybe this is some statistical readings for something. You have equipment 1, equipment 2 to read like some kind of temperature. I don't know, like temperature should be kind of deterministic, easy to, but maybe you have something like more noise is subjected to noise. Maybe you make two observations here, and this observation will be both of them kind of Gaussian, like subject to some Gaussian noise. Added to like additive Gaussian noise to the ground truth there, and then like they will be conditional independence given x, let's say, given the true ground truth there. Then I will have p y1 given x multiplied by p y2 given x here. So again, like these two will be Gaussian, right? So again, I also have a situation like Gaussian multiplied by Gaussian. And say like I can have this one is y1, and with mean, let's say it's like x. I have a covariance matrix like sigma y1, let's say. I have like two equipment, maybe I have different sigma, let's say, right? And I have like another y2, the mean is also x, I say the equipment is like unbiased, the estimation, the detection is unbiased, it's always
That is the mean x?
Yes.
Or maybe we can...
Mean x. Here is assume like a scenario that I have some equipment to measure something. So, and the measurement is unbiased. So it have some noise, right? The noise is some Gaussian noise. But if you measure many times, and you take the average of them, the estimate is always go to the original mean. So that the expected measurement is just the ground truth there is just x there. Yes, but they have the equipment that can both equipment can have different noises. And maybe noise statistics, like the first one maybe have sigma y1, the second one sigma y2.
Is same with x in here. This one x is same with x in here.
Yes.
Or mean the x become mean.
Yes. This is like the PDF of y1, right? The PDF y1 that, as I just mentioned in the example, it will have the mean of the ground truth. I'm trying to make the observation with some equipment from some meter, maybe measure some voltage, maybe that voltmeter have some noise somehow, but it kind of the expected measurement should be just the ground truth, right?
Yeah.
It should be just x. Yeah.
With has variance, and then
have variance, yeah.
Why is Gaussian? Because there is
here we just assume Gaussian, yeah.
Because there is noise.
Of course, you can have other kind of noise, but yeah, we here we are again assume Gaussian.
Thermal noise.
Yeah.
Okay. What's different between this one? Is this y2 also same x?
Same x, but this y2 can be different, let's say.
Or y2 can be different.
The variance, covariance can be different.
Okay.
Yeah.
That's right.
So then let's see how do we multiply this? So
this is actually 0 here. As you mentioned before, this is a probability of this zero. I mean that conditional independent.
No. You mess out the other thing. This is 0. Y y1 minus mu y how do I write that? But I should probably how do I write that? Like I don't know how to write it honestly. So it's something like after observing x, the random variable of y1 minus its mean multiplied by the random variable y2 minus the mu y2, the expectation is equal to 0. That's correct. Yeah, that's the covariance between the two, right?
So that's the covariance between two. When x given, it should be 0.
Yeah, given x, when it's given x. So when you're given x, then you will have a different distribution for y, right? Something like under that.
Why should it be like that?
Oh, why should it be like that? You mean like, okay.
Therefore,
this, if ignore that, this is just like saying that y is independent, right?
Yeah.
So y is like uncorrelated, right?
Yeah.
So when you
independent, y1 and y2 independent.
Okay, this will in general will be this is in general the definition of uncorrelated, but for Gaussian it implies like it's independent.
The first thing, y1 and y2 is independent.
Oh no.
And
Here is not, but you're asking that why is defined like that, right? So therefore I try to explain to you.
Oh, okay. So the first
they are not independent. They are independent
in the
conditional on x.
Oh, yeah, okay. Yeah, and the conditional is this.
Yes, I mean like maybe I can write something like this, but it's very ugly. I don't know how to write it. So y conditional on x, like it will be, yeah.
Yeah, that's right. Yeah. So this one actually is constant.
Yes, this is constant, this is constant. This is a conditional mean given x, right? And this is basically, you remember that's from the equation, this will be something like mu y1 given x is equal to mu y1 minus sigma y1 x, sigma x inverse x minus mu x, right? Something like that, right?
Yeah.
I forgot plus or minus, maybe it's plus.
Before that you write that.
Yeah. This is the mean, right?
Yeah.
I think it's plus. I'm not sure it's plus or minus actually. Probably plus, yeah.
Okay. So, and therefore after that you can use this one because there is this condition. So
yes, because it's conditional independence, so we will just write like this, right? In general,
how to write that?
In general, it's like this, right? y1 given x, y2 given y1 given x, right? Oh, sorry, y1 and x, right? This is always true, right?
Yeah,
this is always true. But then, like, if it's you have this condition here, you have a Markov chain. It means that like something like that. It's y2. So y2 given x, then y1 is not important anymore. So I can remove that. So it becomes y2 given x.
Y2 given x or y1 is not important because
Yeah.
That's conditional independent.
Yes.
Okay. That's right. Actually, that can be write in the mathematical.
Mm.
You can rewrite in mathematical.
Which one?
2d that y. 2d that y1. By include this one.
Oh, I mean, like this is basically, you can, this is more or less the same definition of. So this can be defined as a definition of that.
Yeah.
This is kind of equivalent to py1 given y2x is equal to py1x.
Yeah.
You can show it either way, and this also equivalent to py1 given x times py2 given x is equal to py1 y2 given x.
Yeah, that's right.
Yeah, and of course this one are equal because I just from here, right? We can show using this, we can show. So, but this three is kind of equivalent, and all these three like are conditions like are mathematical conditions to
Yeah.
that characterize that.
Substitute to that.
Yeah.
Yeah. So the first thing is one, and that how to prove that is come from the mutual information.
Of
That
show which one? You mean like show when it's a is
Iyx is bigger than Iyx is bigger than Iyz. I think this is Z.
oh, you mean this whoa is that whoa or I?
This is Z.
Oh, earlier maybe I use C
Oh,
here.
yeah.
Yeah,
This
this
is
is another setup now.
This is Y1. Yeah.
Yeah.
I mean that Iyx is bigger than Iyy1.
Yes.
Yeah.
There's a yeah, but you cannot use that to show this will be like very difficult. I'm not even sure this holds. Only that like this way like definitely is true. Like if like you have this, then you have like that's
Yeah.
the data processing inequality.
Yeah.
Sorry, y1 y2.
I mean that we cannot improve.
Yes.
Yeah. If the processing in there, and then from here can correct this can derive to this one.
From where?
From here, and here and derive this one.
I'm not quite sure. Like this one, you can go to derive this. Actually, I have doubt in that. Like, you need to.
There is a proof. Actually, I saw this in what the books.
Yes.
Yeah.
I mean, yes. I mean, like you have this, you can prove this.
Mm.
But I'm not quite sure there's another way around. Yeah, I'm actually quite sure. Like most likely, you cannot say when this happened, you can show that it's conditionally independent. You probably will need something stronger.
In the what is the book? The pattern?
Coffin Thomas.
Yeah, Coffin Thomas. There is proof that.
You sure like this to this?
No, firstly.
Oh yeah, this of course. As mentioned, that this you have the
Yeah.
proof of course.
Firstly, he mentioned about this first, and he proved this one to here. So it can be reversible. I think we can prove this one first and go to here.
No.
So firstly, that's a component first.
Yeah, this so proof the like we show that even in class, right? This is pretty easy to show. But the other way around, I strongly doubt that. I mean, I strongly doubt that like, there's a
This is
sufficient condition to show that it's conditionally independent.
yeah. This is the basic for to mention this actually.
Yes, this is the kind of like the definition basically for this.
Yeah. Okay.
Or this like any of these representation is the same because
Yeah. It's always the same in the another fashion. Another
Yes.
and
Now let's what? Maybe let's continue. Like now, if we try to multiply these two guys here, okay. So let's only care about the exponent. Right? The exponent will have a form exponential. So if I multiply these two guys, it's proportional to 1/2 x minus, let's see, y1. The mean is 6, right? X minus y1, sigma y1 inverse x minus y1, something like that. I have some transpose, of course. And here I have another term, like x minus y2 transpose y2 inverse x minus y2. And this again, like we can do computing square, right? We try to, you see, like your right side looks like it's a Gaussian, right? You have x. If I can form something like x minus something multiplied by something and x minus something, then I'm done more or less. So I need to compute the square there. So let's see. So let's okay. Let's again use the precision matrix instead of the coincidence. So I have like sigma y1 inverse is equal to lambda y1, and sigma y2 inverse is equal to lambda y2. Then or maybe even this called lambda 1 and lambda 2 is easier. And you see, if I expand that, this is kind of proportional to exponential. I have some minus sign here, minus minus 1/2 x transpose lambda 1 plus lambda 2. That's these two terms here. X, right? This includes the quadratic terms basically. It's like quadratic term is a quadratic equation. Oh, it's kind of expanding that. This is, I just write it as lambda 1. This is lambda 2. Yes, and then I have terms like yes.
This one times this one. That's right.
Yeah.
And so this one times 2.
I have a transpose. Yes, I have transpose that. Yeah.
Transpose. It means that how transpose this one to there also.
Yes. You have x minus y1 transpose will be like x transpose minus y1 transpose, right?
Oh, okay. So like that, and then this one to here and this one to here.
Yeah. Then therefore, like this, the first one x transpose times this one times this. I have this term here, and then like x transpose times this times x here. I have this one here, x transpose times lambda 2 minus x.
Oh, yeah.
So it's like the quadratic terms in a quadratic equation.
Oh yeah.
Yeah.
Yes.
So
So that will be still has remain.
yeah, of course I still have stuff, more stuff. So the more stuff I have this linear term, right? I have like x, for example, I have x transpose lambda. I should have minus term here. Minus y1 x transpose lambda minus y1, and then actually I also have like this is 1/2. 1/2 already outside actually. I have like the other term is like y1 transpose lambda is lambda 1 x
from where?
here x transpose lambda 1 y1
Oh yeah.
and y1 transpose lambda x
X.
So I want to have the linear terms next. So I have 4 terms here. Right? I have like x transpose lambda 2 y2 minus y2 transpose lambda 2 x. Then what next? Then I have some other terms is constant. It doesn't depend on x, so it's like constant. So I can group the other term as a constant and put outside because other terms does not depend on x. So let's ignore those first. Then like this one here, know that like let's see. Maybe I'll copy to the other. I don't have enough space now. Where's now this is what we have up to now. Now this let me group also like this to x transpose lambda 1 y1 plus lambda 2 y2 and minus y1 transpose lambda 1 plus y2 transpose lambda 2 x. So
It's come from where? X.
oh, I just regroup this. So I group this term and this term together to here, and this one and this one to here.
Oh yeah, that's right.
Yes, and x transpose lambda 1 plus lambda 2 x. So let's see, I have exponential minus something like that, minus. Now I need to complete the square. I want to have something like again like x minus something multiplied by something here, x minus something transpose, this is equal to this guy here, more or less, right? This is my goal here.
That's X. That's X. Could be together, could be combined. You want to get X?
I want to get this multiplied together is equal to this guy. Maybe I have to have some other terms, but let's see what I can do. Like maybe apparently I probably need something like that in the middle, lambda 1 plus lambda 2, right? Because I need to get this term back, lambda 1 plus lambda 2 here. I have x some terms to get one of these terms. So I have x. Let's look at this term. So I want to get this term here, right? So if I have x transpose multiplied by this guy and multiplied by something here, I have x. Some terms here should be equal to this guy here. I mean x transpose times this times this should be equal to this. So x transpose times this one time I have add something, let's say add this guy here. So I mean this transpose times this guy here. I want to get this. So what I can have is an option is let's see, we simply have lambda 1 plus lambda 2 inverse, right? And lambda 1 y1 plus lambda 2 y2. Now if I have this, then x transpose multiplied by this guy will get me this one, right?
That's right. Why? If this is one per lambda 1 plus lambda that is 1 per. So this is
Yeah, this is lambda 1. This is lambda 1 plus lambda 2 inverse.
Yeah, inverse it means that 1 per 1 over that.
Yes.
So this is will be cancel.
Yes, that cancel the middle term there.
And then if we times this one,
so I'm then equal to this way. This is just basically copying back this one. X transpose multiplied by this guy multiplied by this guy. This got cancelled will be X transpose multiplied by this way. So therefore equal to this one here.
But where is X transpose in there?
X transpose, I have transpose here.
Or you not yet use?
Yeah.
Oh, okay, that's right.
So then I also have one. Okay, I need the form to be symmetrical.
But this one x, y, lambda 1 times lambda 1. So this is will be lambda 1 power 2.
No, I got cancel here. Lambda 1 plus lambda 2 multiplied by this one here. This 2 got cancelled.
Oh, okay, yeah, that's right. Okay.
Yes.
I forgot. Yeah.
So and this one I can hopefully I want this to be the same, right? Because in the Gaussian form, these two terms should be the same, two expressions should be the same. So if I also copy this one, it's like lambda 1 plus lambda 2 inverse lambda 1 y1 plus lambda 2 y2. Hopefully this is my form, and hopefully this guy multiplied by this multiplied by this one give me this term here, and you can see indeed it's okay, right? Because this one have a transpose, it become like r lambda 1 plus lambda 2 inverse transpose. Inverse transpose is still itself, because lambda 1 and lambda 2 is symmetric. And lambda 1 y1 plus lambda 2 y2 transpose. I think I'm missing a transpose here, I see. Oh no, it's okay. This one is correct. So lambda 1 plus lambda 2. So I mean this term multiplied by this term multiplied by x, right? Then these two guys got cancelled. And this one will become like y1 transpose. Lambda 1 transpose is itself, plus y2 transpose lambda 2 times x. So it's indeed this one here.
Yeah, that's right.
So therefore, like this, we find that this is the exponent. So if we compute the square, then basically what we have is this one here. This is the. So therefore, from here we know.
But you don't know. You don't get this one.
Oh, this one is at the beginning, right? X transpose multiplied by this multiplied by x. I got this way.
Oh yeah. The x. This one. X transpose. This one transpose.
Come on, here. X transpose is here. This is a bracket. I'm sorry for my handwriting. It's a bracket here.
Oh yeah. X transform multiplied by this and
multiply by x. You get this one.
X. Oh yeah, that's right. Yeah. Okay.
So
that's complete for all.
So of course I have extra terms here, like it's like this guy multiplied by this, but it doesn't matter, it's a constant, right? This does not depend on x, so it will just change the normalization factors at the outside, so it doesn't matter. But from here, all this we can see like what is the mean and variance, right? This will be the mean, right?
That is not depend on x and y.
This depend on y.
I mean that if the constants mean that depend on x and y, or only x.
Wait. What okay, yeah, constant normalization only does not depend on x.
Only on x.
Because
not on y.
It depends on y. It doesn't matter because we are looking into like the multiple. It's actually like px. What are we looking at?
So you want to only depend on x.
Yes, because we look at the multiple is to be equal to some. Okay, let's go back like what we are computing really. We're computing this way. y1 x and sigma 1, let's say, or sigma y1 multiplied by y2 x sigma 2. So we would just want to like see what was the multiple we get. So what we're thinking, like when we multiply that, we see like in terms of x alone, it's a Gaussian distribution, right? With some constant. So it's like it will be something like a Gaussian. And you can read the mean here. The mean is what? This term is the mean, right? So therefore the mean is like lambda 1 plus lambda 2 inverse lambda 1 y1 plus lambda 2 y2. And the variance is like lambda 1 plus lambda 2 inverse. Be careful, this is like the variance is supposed to be inverse of this inverse of this matrix, right? So therefore the variance is like lambda 1 plus lambda 2 inverse. And that's but be careful when multiply that, this doesn't necessary to be a PDF. So therefore this normalization factor, like it is not exactly a PDF equal to the Gaussian PDF here. They still have some normalization factor here. It depends on y.
But it's already in Gaussian form.
Yeah, this part is in Gaussian form. It will be a Gaussian form multiplied by some constant.
What is a constant?
Yeah, coming up. But I mean, like this one, we just say like, okay, this is actually the multiple will be this.
So it means that the Gaussian, it is still in the Gaussian and multiplied by something. So it's still in the Gaussian, therefore.
It has a Gaussian form. The form is like a Gaussian.
Yeah, form is Gaussian.
But that one is no longer PDF. When you multiply, when we say it's a PDF, you need to be normalized to 1, right? Yeah. So I mean, if this is a P, if a PDF like Px, dx, this should be equal to 1, right?
Yeah.
But I will have some constant multiplier, so yeah.
So you need to normalize it first.
Actually, we are interested to look at what's the normalization factor also. But you can do this with, I mean, like, probably you can go through the step to try to find the normalization factor, but this is very tedious, right? I will just go for another better way, like to find this. So,
okay.
And so, but you see, like this part here won't depend on x, right? So this normalization factor will depend on y, y1, y2, the oscillation basically, and it can also depend like sigma 1, sigma 2. So if yeah, something like maybe like even mean for y1, y2, but it won't depend on x. So now let's try to look for this constant here, like this normalization factor here. So so remember what we're looking at here. We have this is like a py given x, right? A conditional py1 given x, a conditional probability given of y1 given x here and py2 given x here. So if we consider a picture like this, like if we have assumed that y1 are conditionally independent of y2 given x, or from a Markov chain here like x, y1, y2 and y1 here. Now when we have this multiple here, note one thing, that like this Gaussian distribution is symmetric, right? So in the sense I can, this PDF will be the same as the PDF of taking x as the variables and y2 as mean as well. Right, these two terms is exactly the same.
Why?
Because a PDF is symmetric. I mean Gaussian is symmetric, right? You have the term is like you can go back to just look here. For Gaussian PDF, it will be like this, right? This is a for Gaussian. So therefore, like x, this function here, x y1 sigma y1 is basically equal to like just y1 x sigma y1, right? Because it's just like replacing this x and y1 is just doesn't change anything, right? This is like the quadratic term, like in yes. So, but if we think of that way, this one is similar to a px given y2, right? So this is like you can consider that as like a PDF of x given some observation, or like given some pi of y2. So, and therefore like you have as a whole, like if I copy it here, let me paste here, y1 x sigma 1 multiplied by y2 x sigma 2. As I said, like, I can write this instead of like py1 x sigma 1 and x y2 sigma 2. Now this is like py1 given x here.
That's only y2. You changed it only in y2.
Yeah, I only change in y2. I only change in and this is like px given y2 here.
Why?
Oh, x is a variable and y2 is like some pi here.
Oh, okay.
Yeah, and now because I have the conditional independence here, this guy is actually equal to px y1 y2 also. So if you look at the whole thing, like this is what? This is actually p multiplied that is px y1 given y2.
That's why you create like that.
Yeah, you will see why I'm going to do that. Like, but then okay, I know this form here is equal to, as we showed earlier, it's actually equal to some let's see, where is it? This is equal to some constants times x, a Gaussian x, with mean is equal to what? Lambda 1 plus lambda 2 inverse lambda 1 y1 plus lambda 2 y2. Right? Is that?
That's mean.
Yeah, I think so. Right? Yeah, that's mean, right? And then like variance is lambda 1 plus lambda 2 inverse, right?
Yeah,
so
constant. There's constant.
That's constant. What means is like this is equal to this, right? Because we just said that like I can also think of this another way. Think of this as a PDF. This product is basically it's actually like this multiple is this part, the second term here, is equal to just the conditional probability of x given y1 and y2. So therefore, like this product, like under this step up, is also equal to px y1 given y2 here.
That's the on the right side. It means that for all of this can be right in here.
Yes. Yes. This is equal to this.
Yeah, because the go here.
Yeah.
So that's this time this is this.
Yes. But then it's so why I want to do that? You asked me like why I want to do that. Now it's very nice because now I can try to integrate both sides with respect to x, right? Now if I don't have this constant here, it's like this is just a PDF integrate over x. This is just equal to 1, right? So if I integrate both sides with x here, or like integrate this side here with x here, I should just get the constant, right? If I integrate this side, okay, let me recheck. So if I integrate the left-hand side with respect to x here, I should just get the constant I want to search for. For the right-hand side, if I integrate over x here, I should just get like py1 given y2, right?
y1 given y2.
Yes.
Because that x on the disappear. Yeah.
Yes.
Integrate. So that is a constant as k.
So the constant is just equal to py1 given y2
Yeah.
under this setup basically. So but under this setup, what is py1 given y2?
Given y2. Yeah, that's Gaussian y2.
Yes. Here like you have this is like x is like a Gaussian random variable that have a mean y. Let's see, where is it? With mean y2 and with some coincidence x similar to right? And then like y1 is like a Gaussian variable with mean x with some variance similar 1, right? So therefore, if you think of like what's y2, what's y1 given y2, is basically it's just it is a Gaussian random variable with
If we use the property of Markov, that would be y1 given y2. It can be any. Can be 0.
No, it's equal to this PDF, right? This is PDF like y1 given y2, right?
So y1 is actually this one. This one. That's right.
That's the PDF for that.
Yeah, PDF for y1. That's one.
Yeah, PDF of y1 given x, but be careful, this is PDF y1 given x.
Yeah, given x, and now y1 given y2. So that's PDF.
First, yeah, this is a PDF. First look at like what's the PDF look like. So it will be something like the
y1 given y2.
what's the mean?
It means that y1 given y2 here.
Or let you think of that like this. If I interpret this term, this is a PDF of y1, right?
Yeah.
Of something y2. And this is a kind of PDF, in any case, it's a PDF for y1, right? So, and for this PDF, it has a mean, some mean, right? And may have some variance, right? What's the mean for this PDF here? Look at this picture again. So, the relationship of x, like, given y2 is basically, x is some random variable here, is some random variable with mean y2, right? And then like you have some coherence here, like similar to here.
Yeah.
And then what's y1? y1 now is actually some random variable, again some normal random variables with mean x and coherence sigma 1, right? So for y1, kind of given y2, the means should be just simply y2, right?
Should be y2.
Yeah, should be just y2 because right the mean for this distribution for y1 given y2 will be simply just equal to y2, right? Because when you look at the mean of y1 here from this part here, the mean for y1 is x, right?
Yeah.
And x itself is a random variable, but x takes a mean of y2, right?
Yes, that's right.
Yeah, so therefore the mean of y1, if I ignore x there, like x is gone, that will be simply y2, right?
Yeah.
So therefore the mean is y2.
Yeah.
Now how about the covariance? Covariance will simply the addition, right? Because you have one noise. It's like here, this Markov chain is actually like you have added noise 2 times. First, I have start with some observation y2 or like some ground truth y2. Now you have some noise that's subjected to some this noise, and that noise variance is a sigma 2. And then like again you add another noise subjected to noise sigma 1.
Can you
Oh, okay. And okay, this x here is like y2 added with like some Gaussian noise of sigma 2.
Added Gaussian noise.
Yeah, additive Gaussian noise of sigma 2,
Yes.
assuming Gaussian noise, right? Have a mean y2. If you have you can think of like has a mean y2 but have an additive Gaussian noise, assuming additive Gaussian noise of sigma 2,
Yes, that's right.
right? And then like for y1 is have the same case. Y1 can think of like is x, I have a mean x but have additive Gaussian noise sigma 1.
Yes.
So then if I coming from directly y2 to y1, that would be just like add two noises, right?
Yeah,
If I from one, then it would be like it's simply the variance is simply sigma 1 plus sigma 2 covariance.
Yeah, that's right. That's I had to because that this will be
Yes.
there. This one is sigma y1 and sigma y2. So
Yeah. Sigma y1 is sigma 1. I just shorthanded that. Sigma y1 is sigma 1. Sigma y2 is sigma 2.
Okay. And then will be the variance will be at of
And this PDF, right? So PDF with a mean, this one variance for that. And I'm asking what's the value when I take a value y1 is simply like this, right? So therefore, this is the constant. So we immediately have the constant.
what
So
is the constant?
This is the constant.
That is a noise. Yeah, that is the Gaussian.
This is Gaussian, but this is the constant. Constant meaning this is the normalization factor that we are looking for. This is k.
Yeah, that is K.
We say that k is equal to p integrate of px y1 given y2 over x, right? And this is equal to this guy, right? And this guy is actually just equal to this guy, right?
Yeah, so you mean that this is the constant for K?
Yeah, that is the constant. And this
The K is not constant. I mean that
is a
K
constant. It's constant with respect to x, but not constant with respect to y1 and y2.
Yeah.
Yes.
Right. Yeah.
So therefore, like
So that is a PDF also. The constant is PDF given y and
yeah, it looks like a PDF form. So therefore, like finally, we have the result is like this.
Yeah, result of times that to that.
Yeah, that's actually like I have like this
To that.
y1 x sigma 1 or like or we use that sigma 1 times y2 x sigma 2 is equal to this constant y1 y2 sigma 1 plus sigma 2 and times that is a the mean is a x, the mean is a y lambda 1 plus lambda 2 inverse lambda 1 x plus lambda 2 lambda 1 y1 plus lambda 2 y2 and the variance is like lambda 1 plus lambda 2 inverse. Yes, that's what we have. It's very interesting because you can interpret lots of states. I mean like that's it looks complicated, but you can kind of interpret like many of why you have an expression like this, because if you think of like multiply this, what's the mean? The mean is actually like a weighted sum, right? You have observation. You want to estimate x now, the likelihood of x now. After you make observation y1 and y2, the overall observation, overall estimate should be the weighted sum of y1 and y2. Right? This is basically just a weighted sum.
Yeah.
And of course, this is more complex because it's vector form, right? So, but it's still a weighted sum, right? You have lambda 1 is lambda 2 is basically the weight here.
Weight.
Yeah, it's a weight. Yeah.
That is actually the
It's like
covariance.
it's like something like a plus b, right?
And
Something like that.
lambda is covariance. Sigma.
Lambda is not covariance. Lambda is inverse sigma.
Yeah, inverse sigma.
Lambda is a precision. So that's why it's even more. You can. That's everything is very natural and intuitive. Like you should weight it in the sense that if lambda is bigger, okay. Of course, I'm hand waving this because in general this matrix, right? If matrix, when I say bigger and smaller, it's a little bit hand waving. But still, like if you think of scalar, then I can talk about or like if a matrix, you can think of like it's bigger in terms of the eigenvalues or something like determinant. But when this is bigger, then what precision means is like the observation is more precise, right? Because this is the precision for that observation, right? If that observation is more precise, you should give more weight to that.
Why you say that observation is more precise?
Because I remember where was lambda 1. Lambda 1 is sigma 1, sigma 1 inverse.
Yes.
And the inverse of the covariance. And this is an inverse of the covariance of y, the observation of y. Yeah. So,
times that inverse of covariance of y, 1, that will be more precise.
So therefore, like covariance, like if it's bigger, the covariance it will be like it'll be basically, or like if you think of in the 1D case, it's more intuitive. So if your variance is bigger, it's less certain, right? So therefore, your precision will be smaller, right? On the other way around, if your variance is smaller, then your precision is bigger, right? So then, therefore, you are basically weighted by like how precise your observation. If your precision is like higher, then you weight it more, right? So it's extremely natural here. And then the new variance of the observation will be just
precision.
Yeah, or like you can think of like now if you in terms of interpreted this in terms of precision, we'll be basically saying that like the new precision will be the sum of the precisions of the observations, right? Your also first observation have this precision, second observation have this precision, then the total precision is just the sum.
The sum of the variance that.
The sum of the precision. Actually, precisely the sum of precision, because the precision of the new observation will be just like the inverse of this guy, or inverse is covariance matrix. So therefore, it's just the new precision is just lambda 1 plus lambda 2. So therefore, like the
new variance, the new sigma is lambda 1 lambda.
Yes, I see like I'm comparing over time again. So
this will be bigger than before. The variance will be bigger than before.
Variance will be
bigger. There is
no, actually variance will be smaller because your precision will be bigger, variance will be smaller. Yeah,
because that inverse that in that
yes.
Should be inverse. Okay.
And even this term have like some reason for that. Like it's very nice, the scaling factor. You can think of the scaling factor as like now you how compatible like these two observations, right? So if these two observations is very compatible, this value will be big. If it's not so compatible, then this value will be small. So how compatible will be based on like.
What do you mean the compatible?
I mean like for example, if you make some for example in 1D case, I have a reading like ground truth is 100. Maybe I make one observation. He's like here is 80. Another observation is like 120. Maybe it's like quite a bit far away, like two observations. Now I would be not quite certain that whether they are correct or not. But if I have like observation one is here like 95, the other one is like 1/5. These two observations looks more like reliable. So and of course like this is relative, right? Depends on the unit, right? Depend on the distribution. And the nice thing here is also like if you have the variance of your observations from the beginning, then you can interpret that like much more. Not something you try to guess that. Like of course you need to determine how do you know this variance to begin with. But once you know that, then this is kind of pretty I shouldn't say straightforward, but pretty reasonable, also like pretty intuitive.
Yeah, it's meant that. So, but this is Gaussian and times Gaussian, so we cannot make it in the one patient, in the one form. We cannot make it.
Okay, I guess we should discuss this ending this first. This is I guess we'll just stop here for now, then I will come back later.